Welcome back to Chapter 1, Lecture Part 3. So far we have learned about science, we've talked about chemistry, we have defined science and technology, we have looked at the scientific method, we went ahead and described the importance of green chemistry, sustainable chemistry, and we also did few definitions on scientific method like hypothesis, scientific law, scientific theory. We learned about scientific models and explained their relationship in science. Then we went ahead and talked about risk and benefit and risk and benefit analysis. Uh, then we transitioned to defining matter, and we went ahead and talked about mass and weight and did the classification of matter. And today we are moving forward and we are going to learn about measurements of matter. In chemistry, we use units, which are basically standard quantities used to specify measurements, and it's very critical because we do accurate measurements of properties such as mass, volume, time, and temperature, and they are important aspects of scientific data, collecting scientific data. So here, the two most common unit systems are as follows, like the metric system, which is used mostly in the most part of the world, and then we have the English system, which we use commonly in United States. So you all are used to hearing about inches and foot conversions, or you have heard about pounds, ounces, gallons, etc. Scientists use international system of units called the SI system, which you see here on the table, which is based on the metric system. This gives people all over the world some standardization that they can follow. So here are the 7 SI base units. The most commonly we will be using length, mass, time, temperature, and the amount of substance. If you continue with chemistry, you will learn about electric current and luminous intensity as well. But the most common are length, mass, time, temperature, and amount of substance, which chemists measure in moles. So as we learned about the SI units, remember that the SI units are based on the decimal system, and it's easy to convert from one unit to the other. Here on the table, you see different things. So you see approved numerical prefixes, then you see exponential expressions, and you see the decimal equivalent of that. And because they are such big numbers, we make use of these prefixes because it makes our life simple. So why do we use such exponential expressions? Because scientists often deal with a range of sizes. So we could be working with objects which are smaller than atoms, and it could be as large as universe. So we use this exponential notation to describe the sizes of such objects. So here are the exponential expressions. So let's just start with 10 raised to 1. So everyone knows that 10 raised to 1 is equal to 10. So that's the base. And then 1 divided by 10 will be 10 to the power of -1 or 0.1, which is referred to as the deci, and the symbol is small d. 1 divided by 100 is 10 to the power of -2, or 0.01, which is centi, represented as C. And so on and so forth. So 1 divided by 1000 will be a milli, represented by M here, and so on and so forth. So you have micro, which is 10 to the power of -6, nano, which is 10 to the power of -9, pico, 10 to the power of -12, and femto, which is 10 to the power of -15. So that's 1 divided by the powers of 10. What happens when you multiply it? So 10 raised to 1 is 10. So 10 to the power of 2 is 10 times 10, which is 100. So that is hecto. Then 10 times 10 times 10 is 10 to the power of 3, or 1000, which is kilo. And then you have 10 to the power of 6, which is mega, 10 to the power of 9, which is giga, and 10 to the power of 12, which is tera. And we all in today's world use these giga and terabytes of storages, right? To store our pictures, videos, and other information. So this is what these prefixes means. So basically they're used to express small sizes, a range of sizes, like from a small object to very large object. So let's review the 4 common measurement units of matter. First is mass. So the SI base unit of mass is kilogram. Remember, 1 kilogram is about 2.2 pounds. And by the system that we learned some time back, we learned that the prefix kilo, or this K here, means 1000, right? So 1000, or 10 to the power of 3. So remember that kilo is bigger than the base unit, or is a bigger quantity than the centi or the milli that we saw. So 1 kilogram is equal to 1000 grams. So 1000, or 10 to the power of 3 grams, is 1 kilogram. And if we consider the milli, so 1 milligram is equal to 1 divided by 1000, right? Milli meant 10 to the power of -3. So this will be 10 to the power of -3 grams. So this is how we can also use these prefixes for unit conversion. The next unit is length. So the SI base unit of length is meter. So consider this: 1 kilometer is about 1000 meters, and in the lab, for the lab purposes, we find these lengths. Or meter is a big length, so we work with smaller lengths than the meter for our convenience. So we use units like centimeter, which is 1 divided by 100, or 0.01 meter, or 1 millimeter, which is 1 divided by 1000, which is 0.001 meter, or 10 to the power of -3 meters. So you can go from meters to centimeters or millimeters, which is commonly seen in the lab. and you will also go through this in the lab, in your lab experiment. Volume, so length actually can be used to derive area and the volume. Um, Remember, area is square meter or millimeter, so it could be expressed in centimeter square or millimeter square in lab. And volume is expressed as cubic meter here. So here's cubic meter here. And in the lab, we also use cubic centimeters, which is cc, also referred as cc, or cubic decimeters. So cubic decimeters can also be used. And remember that most commonly we also talk about liters. So remember that 1 liter is equal to 1 decimeter cube, which is equal to 1000 centimeter or cubic centimeter or centimeter raised to 3 cubic centimeter. So 1 milliliter, which is another unit which is commonly used while measuring volumes in the lab. So 1 milliliter is also referred to as 1 cubic centimeter or 1 cc. So you might hear that that term. Sometimes people say, how many cc's of water? That means how many cubic centimeters of water. In other words, how many milliliters of water. And the next we have is time. So the SI base unit for time is seconds. And in labs, people measure time in milliseconds or in microseconds, nanoseconds, picoseconds. So all those prefixes can be used in front of the seconds to measure different time intervals. So we learned about these SI units, and we learned about these prefixes and the power of tens, and they can all be used for problem solving and for estimation. So one such example is here, which says convert each of the following measurements to a unit that replaces the power of 10 by prefix. So here you have the first value, A is 2.89 times 10 to the power of negative 6. So you should know from the table that we looked at, the prefix table, that 10 raised to minus 6 means something. So you could replace that with the prefix. So we know that 10 raised to minus 6 is micro. So you could express this as 2.89 micrograms just by knowing what each unit means, or what is the prefix in terms of powers of 10. So I want you to try the next one, which is 4.30 times 10 to the power of negative 10 to the power of 3 or 10 raised to 3 meters. Please pause the video and try to solve this. So here's the solution. So as I said, 10 raised to minus 6 is micro, so you could express it as micrograms, and 10 to the power of 3 is kilo. So it's a kilo unit. The unit is meters, So you could say it is 4.30 kilometers, which is the unit of length. And here you see how these small measurements or these prefixes gives you know opens up a new field. So nano world, nano here means 10 to the power of -9, or imagine 1 billionth. So nanotechnology is a field of science where you study to manipulate matter at such small scale of 10 to the -9 scale, which is equivalent to the atomic or molecular level scale. Here on the slide you see a carbon nanotube, and you see these black or the gray circles or gray balls are the carbon atoms which are bonded in the hexagonal pattern here. So you can see one hexagon bonded to the other, and it forms this hollow structure which gives which allows for potential applications in various fields. And these nanotubes, or the carbon nanotubes, are about 100 times more stronger than the steel, and they're expensive to make, but they have huge potential of being applied in different fields. And now we transition to the topic of density. So here everyone needs to learn what density is, understand what it means, how do you calculate density. So density is defined as the amount of matter in a given amount of space. So here you have D, which is representing density, equal to mass over volume. So M over V, M represents mass, V represents volume. And on the picture here on the scale, you see a cube of copper which has a side that's measuring 1 centimeter, and it's weighing 8.94 grams. So you have the mass, which is 8.94 grams, and the volume, which is in cubic centimeters. So 1 times 1, because this is the cube. So 1 times 1 times 1. So you have cubic centimeters, which is equal to 1 cubic centimeter. So 8.94 divided by, so the mass divided by the volume of the copper cube will give you 8.94 grams per cubic centimeter. So that's how you would calculate density. Now pay attention to this equation, which is density is mass over volume, or mass divided by volume. Once you know this, you could manipulate this equation. So you could be given the two quantities out of the three here. So you could be given mass and volume, as we saw in this example, and you were able to calculate the density by using mass and volume. Now you could be given density and the volume and be asked to find the mass. So in that case, mass will be equal to density times volume, right? Or you could be given mass and density and asked to find the volume. So in that case, volume will be equal to, you need to rearrange. So the volume will be equal to mass divided by density. So I usually ask my students to remember one and then use cross multiplication or dimensional analysis to you know find the remaining variable. So you could basically derive these two formulas or equations from density is equal to mass over volume. So you could be asked either to calculate density or to calculate mass or to calculate volume. And please practice the problems related to this equation um, and be comfortable doing that. I will be showing you one example, and then there are some examples in the book and also in the homework. So here's a practice problem that I talked about, and it's asking you to calculate the density of a metal, a sample with the mass of 18.96 grams. So mass is given and the volume is 4.31 cubic centimeters. So the first thing that you need to know here is, what is it asking me to find, and then what is given to me. So mass is given and volume is given. Then think of, do I know any equation, or did I learn something about density where I could use mass and volume to find the density? And yes, you just saw it in the earlier slide. So density is defined as mass over volume. So now you substitute the mass, which is 18.96 grams here, and the volume is 4.31 grams here, and do the math. So divide mass over density, a mass over volume, and calculate the density, which will be like this, 4.40 grams per cubic centimeters. In practice problems, I would prefer students to pause the video and try to solve it along with me, or to try to solve it by yourself and then check the answers. That will help you grasp it and also know if you are missing any point or where do you need to work on. So we have arrived at the last portion of chapter 1, which talks about energy in terms of heat and temperature. So we will learn to distinguish between heat and temperature, and also learn the scales and some problem solving related to that. So we know chemistry is a study of matter, and whenever there are physical and chemical changes that the matter undergoes, it's almost always accompanied by some changes in the energy. So energy is the ability to change the matter either physically or chemically. And the two major forms of energy that you might have read or even heard about are potential energy and kinetic energy. So potential energy, think of it as a stored form of energy, and kinetic energy is something in motion, the energy that is generated because of the motion. Heat and temperature are two concepts in the science which are related, and sometimes people confuse between the two. So think of heat as energy which is being transferred from a hot object to a cold object. So imagine you place a ice cube in your hand. So the heat energy is being transferred from your body to the cube of ice, and it melts it. Temperature, on the other hand, is the average kinetic energy of the atoms or molecules that make up an object. In simple words, think of temperature as a measure of how hot. So you could measure how hot or how cold an object is. Okay, so that could be measured by temperature. So heat is often measured in terms of calories or joules. These are the two common units of heat. And 1 calorie, and take a note of calorie here. 1 calorie with the small c is the amount of heat which is required to change the temperature of 1 gram of water uh, by 1 degree Celsius. So that is what 1 calorie is defined as, and 1 calorie with the small c is equal to 4.184 joules. So this is one conversion, unit conversion that can be used. Everyone has heard of food calories, and notice here calories is the food calories that we talk about has a capitalized C and is actually a kilocalorie. So 1 calorie is equal to, or food calorie is equal to 1 kilocalories. Remember, kilo is a prefix for 1000, so which is equal to 1000 calories, which was the heat energy that I showed you in the earlier slide. And what did I say? 1 calorie with the small c is equal to 4.184 joules, right? And now we are defining 1 food calorie. So with the capital C, and which is equal to 1000 calories, the small c. So 4.184 times 1000, and that's why it is equal to 4184 joules. So remember that. That is the food calorie that we are talking about. So let's look at a problem on energy conversion and apply what we learned. So when 1 gram of gasoline burns, it yields about 10.3 kilocalories of energy. So 2 unit mass is given to you, and the kilocalories of energy is given, and it's asking you to find the amount of energy or the quantity of energy in kilojoules. So what do we know here? So first thing that we know here is we know that 1 calorie is equal to 1 kilocalories is equal to 1000 calories, right? We just learned that because kilo means 1000. So 1 kilocalorie means 1000. And also we know that 1 calorie was equal to 4.184 joules, right? So we learned that as well, and they want us to find out the answer in kilojoules. So again, we know that once we have joules, we can easily convert joules to kilojoules, right? Because we know that 1 kilojoule is equal to 1000 joules. So we know this equation as well that we can use in our unit conversion. So let's start with what we know. So we will start with 10.3 kilocalories, and so we will go from kilocalories to joules. So we will go from kilocalories to calories to joules to kilojoules. So let's see the solution here. So we begin with 10.3 kilocalories. So 10.3 kilocalories times, we know that 1 kilocalorie has 1000 calories. Actually, there is a typo here. It should be 1000 calories. So not kilocalories here. K should be taken away. So 1 kilocalorie, forget this K. So one kilocalorie has 1000 calories. So that in this process, we cancel kilocalories and kilocalories. And we also know that 1 calorie is equal to 4.184 joules. So now we have calories on the top and we want to go to joules. So we express it in terms of unit conversion, or a unit conversion factor, which is 1 calories over 4.184 joules. So we cancel the calories with calories, and now the next unit, now we have our quantities in joules. We will go one step further and use our joules to kilojoules conversion. Now we want our answer in kilojoules, so we will have kilojoules on top. So we know that 1 kilojoule is equal to 1000 joules. So here we use this equation like that: kilojoules on top, joules on the denominator. So joules and joules will get cancelled, and now I have my desired unit of kilojoules here, and then I do the math. So 10.3 times 1000 times 4.184. So take everything which is on the numerator in a bracket, divided by everything in the denominator. So basically you just have 1000 here, so 1000 and 1000 will get cancelled. So you're basically left with 10.3 times 4.184, which will give you 43.1 kilojoules. Here we will look at the different temperature scales. So remember, temperature is a measure of how hot or cold an object is, and it is measured with the thermometer, right? Everyone has measured temperature somewhere in their life so far. So the three common scales that are used are Fahrenheit here on the left hand side, then the Celsius and the Kelvin. So remember, this is the SI base unit. The Kelvin is the SI base unit of temperature, and in the labs we use even degree Celsius. So this is degree Celsius, and Fahrenheit is commonly used in United States. So the way I want you to look at it is like this. So let's look at freezing point of water. We all know that water freezes at 0 degrees Celsius or at 32 Fahrenheit, and that is equivalent to 273 Kelvin. So that's the conversion. And then another point here is boiling point of water. We know that water boils at 100 degrees Celsius, which is equivalent to 212. And if we look at the Kelvin scale, because 0 was equivalent to 273, so if we have 100 degrees Celsius, we add 273 to that, and you have a 373 Kelvin. So basically added the 100 over there. Another important point here is 0 Kelvin corresponds to negative 273 degrees Celsius, and that is referred to as the absolute zero. So you can't go below that temperature in the labs to measure things. 0 degree 0 Kelvin is the absolute temperature. You are expected to know Celsius to Kelvin conversions in the class. So Kelvin is degrees Celsius plus 273, and to be very precise, sometimes the book uses 273.15, so we will use that as well. So let's practice a problem on a temperature conversion. So we know that human body temperature is, a normal human body temperature is 37 degrees Celsius, and if you have to convert that to Kelvin, what would you do? So remember this equation here. So degrees Celsius is 37 degrees Celsius, and you add 273.15 to get to Kelvin. So let's look at the solution. So Kelvin will be equal to degrees Celsius plus 273.15, and that will give you 310, about 310 kelvins. So the last slide here talks about how to use critical thinking to evaluate a claim or a statement in science. So there is a test called Flair's test, where this acronym Flair's comes from, F comes from falsifiability, L is logical, R is replicability, and S comes from sufficiency. So if you have to test the validity of a claim or a statement, for it to be true, it has to pass all these four tests, and still it could be proven false with the new evidence or new data to support that claim, or defy or deny the claim. And if it fails even one of the tests, then it's likely that the claim is false. So I want you to just know that this is how critical thinking and the validity is done. So this basically wraps up our chapter 1. I will post more slides on the appendix A or AA, and that might review some of the topics again in detail, but this is it for chapter 1.